particles. Good. So then I got it, and now I don't know how to take away. Wait a second. Let me take away this. I cannot do it. So now for some reason your okay, so give me a second. I need to I'm stuck now. I don't know why. Can you hear me?
Yes, I can hear you. I
Yes.
don't know if it is the internet connection problem or I don't know.
No, it's a problem. Got it. Okay, very good. So you know when you started to record, suddenly appears a message in my screen that I couldn't take away. Okay, now let me do it again. Okay, very good. So, and I'm going to talk about the Higgs sector, of course. Yeah. In this talk, as you know, then the Higgs is connected to the mass mystery. So in the standard model, simply connected with the vacuum expectation value of the Higgs, the origin of masses, we assume a particular potential that is normalizable. And we know that the vacuum expectation value of the Higgs particle is about 246 GeV. And from that vacuum expectation value, we obtain masses of all particles proportional to the coupling of those particles to the Higgs particle. For instance, the mass of the fermion is proportional to the coupling of the fermions times the vacuum expectation value. So the mass of the W and Z bosons are proportional to the respective gauge couplings. And of course, there is no direct coupling of the Higgs to the photon and the gluon, and therefore they remain massless. Now, we have tested the Higgs hypothesis looking for the Higgs boson at LHC. This is well known. So then, and we had different production channels. The main production channel, as you know, is the gluon fusion channel, mediated by top quark loops. But there are other important channels like the associated production of the Higgs with the WZ bosons or weak boson fusion, and one or associated production of the Higgs with top quarks. And the nice thing is that once we produce the Higgs, we can explore its couplings to different standard model particles. And I plotted here the branching ratios of the Higgs, and the mass that we measure, about 125 GeV, is a very good mass. We're just testing the couplings of the Higgs to different particles, simply because the branching ratios are sizable for many of them. If we had a mass that would be about, for instance, 160 GeV, only the W and Z boson particles will be accurately tested. So, however, for 125 GeV, we are able to test the coupling of the Higgs to botons, to tau, to all the third generation particles, and including the loop-induced couplings to gluons and photons. Yeah? And as you will see, we are starting to test also the coupling to the mixed coupling to Z and gamma. Yeah? This is well known. So then the open question is the Higgs is the standard model one. So this could be tested, for instance, in the so-called kappa framework, where kappa denotes the coupling that we measure in these processes with respect to the standard model coupling. And all the measurements suggest that the coupling, at least to the third generation particles, top, bottom, and tau, as is depicted here, the loop-induced couplings to gluons and photons, and the couplings to gauge bosons remain within a few tenths of percent of the couplings that we expect in the standard model. Therefore, this value of kappa is very close to 1. And another way of depicting this is the linear relation between the masses of the particles that we know and the couplings that we determine with respect to the Higgs field. And as we said before, there should be a linear relation because all the masses are proportional to the coupling to the Higgs field. And indeed, that linear relationship is fulfilled. Yeah, measure. So here I just represent the fact that there are two experiments. So the Atlas and CMS, both of them agree that once we consider the statistical and systematic errors, all the couplings that we measure are within the 2 standard deviations away from what we expect in a standard model. And the interesting fact is that we are starting to test the couplings to the second generation, like the muon, and also these mixed couplings to Z and gamma. And again, all the couplings remain within the expectations of the standard model. And again, this is the same depicted in a linear plot. So observe that Atlas starts to put a bound on the Charn coupling. That is also very interesting. So to complete the second generation couplings, again, the errors are very large, but so far we haven't seen any striking deviation from the expectations of the standard model. Yeah. So in a sense, we should not be surprised by disagreeing with standard model because there is a well-known and amazing property of the standard model and as an effective field theory that if you take any sector, you add to standard model any sector who gauge invariant masses, we do not involve the Higgs, for instance, a new scalar or a new vector like boson, fermion. So there is a theorem that calls the Apel-Carrazzone, the coupling theorem, that says that as we push this gauge invariant masses up, the low energy effective theory will reduce to a standard model. And the speed of the coupling depends on how these sectors couple to the standard model. And in general, if you take a coupling kappa to the standard model, so then the speed of the coupling is regulated by the coupling square of this new sector to the standard model divided by the masses of these particles. And if it is this ratio is much smaller than 1 over v, the vacuum expectation value of Higgs, then all the effects in standard model tend to decouple. So then obviously, then this involves only particles that have gauge invariant masses, so their masses have nothing to do with the Higgs field. If you add masses that couple to the Higgs, so particles that acquire masses through the Higgs, the coupling will not work. Yeah. But what it seems from the measurements that we are getting, it seems that this maybe there is new physics, but this new physics should fulfill this approximate decoupling rule. Yeah. And these properties are behind the whole effective field theory program that became popular in latest years, where people add to the standard model effective higher dimensional operators suppressed by new mass scales that are related, presumably, to the masses of the new particles. Now, this is so a reason why we should not be surprised. So perhaps there is new physics, but as I said, this new physics has nothing, their masses have nothing to do with the Higgs. And then we'll see a decoupling of these new particles fulfilling these rules. Now, on the other hand, we should be surprised a little bit due to the fact that the Higgs potential suffers from a problem of stability under ultraviolet corrections. So if you add new particles that couple in some way to the Higgs with couple kappa, as I denoted before, there will be corrections to the Higgs mass parameter that are proportional to the masses of these new particles, proportional to the coupling kappa square, and at most suppressed by loop effects. These are physical corrections that are regularization independent, and shows that unless the new physics is lighter than a few TeV for couplings kappa further one, so then we will have a problem of stability of the Higgs potential associated with it. And this is particularly true, this problem of stability, in models where you try to connect the Higgs with the ultraviolet physics, like Gran-phi theories, because there the masses will be much, much larger than the Higgs, and one will wonder how do we recover a mass parameter of the Higgs of order the TeV scale if there is a large or heavy new physics. Yeah? So in such a case, we need a delicate cancellation of these corrections that only an extension like supersymmetry can provide. So therefore, the message of this is that maybe it's the coupling of new physics, but that the coupling cannot happen with arbitrarily large masses. So if there is new physics, that new physics is expected to be in a certain range where maybe the coupling occurs, but the corrections to the mass parameter should not be very large. So in this talk, I will parameterize the corrections to the standard model properties in the simplest extension that you can imagine, in particular, the two Higgs doublet model. And even when you add an additional Higgs doublet, the potential becomes more complicated than the standard model, in the sense that instead of having one single quartic coupling, you can have 7 different quartic couplings that I denote here in this potential. So you have a mass parameter that involves the two Higgs doublets, so 2 mass parameters, one that mixes the two Higgs doublets, and then the 7 quartic couplings. The two obvious ones are what I call lambda 1 and lambda 2, that are simply quartic couplings of the individual Higgs doublets. Then there is these two couplings, lambda 3 and lambda 4, that are simply the product of the invariant phi 1, phi 1, and phi 2, phi 2, and the phi 1, phi 2 that appear in mass parameters times the Hermitian conjugate. But there is also all these couplings, lambda 5, lambda 6, and lambda 7, that involve, that are not real. So involve the necessity to add the Hermitian conjugate to the potential. So, and are products of the invariance of phi 1 and phi 2 with phi 1, phi 1, and phi 2, phi 2. And as you can see, they will play a relevant role in the phenomenology that I will describe later. So in generic two Higgs doublet models, it's useful to add a parameter that is tangent beta, that is the ratio of the vacuum expectation values of the two Higgses. The two Higgs doublets can acquire a vacuum expectation value, contrary to the standard model case where there's only one Higgs. And therefore, we need to introduce this parameter. Now, once you introduce this parameter, it's very useful to go to something that is called the Higgs basis. And the Higgs basis is simply a redefinition of the Higgs doublets, simply by doing combinations that allow you to define one Higgs doublet that we call here capital H1, that acquires vacuum expectation value, while the other one does not acquire vacuum expectation value. And that is done by a rotation parameterized by this angle beta that we defined before. Simply H1 will be phi 1 cosine beta plus phi 2 sine beta. And in that case, you obtain these combinations, as I said, with the properties that one acquires vacuum expectation value and the other not, where V is simply the square root of the sum of the squares of V1 and V2. Now, if you do this, the field phi 1, 0, so is therefore associated with field direction that acquires vacuum expectation value, and if the mass eigenstate will coincide with phi 1, 0, this mass eigenstate will have standard model-like properties. Now, the behavior in general of the mass eigenstate, the physical mass eigenstate, will depend on the how much this mass eigenstate will differ with respect to phi 1, 0. So the angle, if you want, in Higgs space, in field space, that parameterize the difference between the physical states and the standard model state phi 1, 0. So, and that angle, we tend to call it sine beta minus alpha, beta minus alpha. Sine beta minus alpha close to 1 will tell us that the light Higgs state, that here I denote as little h, will coincide by phi 1, 0 and will become standard model-like. And cosine beta minus alpha denotes the mixing of this physical state with the non-standard Higgs, denoted by phi 2. So in general, if I go to a Higgs basis, I can define the mass matrix that is parameterized here by these quartic couplings. These couplings set 1, set 6, etc., are simply the same as the couplings lambda that I defined before, but in the Higgs basis. So imagine that you replace lambda by set, and the phi 1 and phi 2 by H1 and H2. The coupling set 6 in particular will be the one that has 3 powers of H1 and H2. And when H1 acquires vacuum expectation value, assuming that H1 is the only one that acquires vacuum expectation value as we did in the Higgs basis, that will provide a mixing between the standard and non-standard components H1 and H2. Make sense? While the coupling set 1, that is phi 1 acquires vacuum expectation value, will be the one giving a mass term for H1, for the Standard Model Higgs. So therefore, while other couplings will refer to the masses or mixing of the non-standard Higgs bosons. So here is the generic form, therefore, of the mass matrix. As I said, set 1 relates to the mass of H1, that is the Standard Model Higgs. Set 6 denote the real parts of set 6, denote the coupling of phi 1, 0 with phi 2, 0, that is the standard and non-standard CP-even components of the Higgs. And you know that there is an imaginary part that then subsequently I will set it to 0, that is related to CP-relating effects, mixing the third component that is related to the CP-odd component of the non-standard Higgs bosons. And observe that there is no CP-odd component associated with the Standard Model Higgs, simply because that is the goldstone that doesn't mix with the other states, at this level. So therefore, if I want to have a Standard Model like Higgs, I demand that it doesn't mix with the other Higgses, and for that, this coupling set 6 should be equal to 0. So if I have set 6 equal to 0, if I have this coupling in the Higgs basis, what I call here lambda 6 equal to 0, there will be no mixing between the standard and non-standard Higgses. So therefore, this parameter, cosine beta minus alpha, that denotes the mixing of the standard and non-standard Higgs, so will be proportional to set 6. And if I assume that there is no CP violation, that all what is here denoted as the imaginary part are equal to 0, the cosine beta minus alpha will simply be given by minus set 6 b squared over the mass of the non-standard Higgs boson square. And the coupling will occur when set 6 b squared is much smaller than mh squared. And as I said, set 6 will denote the coupling that before I call kappa square of the non-standard Higgs sector with standard Higgs sector. And you see here an example of the coupling. The coupling will occur when MH is very large and capital H is very large compared to the standard model mass MH. And therefore, all the effects of mixing with a non-standard Higgs sector go to 0. Are there questions so far? Good. So this is a question of the coupling. And second, while in the alignment limit, the real part of set phi contributes to a splitting of the two heavier mass sign states, its imaginary part so contributes to the splitting of their mixing, so via their mixing. So therefore, the other states that you can have here that are the would-be CP-even and CP-odd Higgses, so are simply given by related to a charge Higgs mass that appears in this spectrum, plus combinations of set 4 and set 5. But what is important here is the coupling set 6 that regulates simply the mixing of the standard and non-standard Higgs sector for the rest of my talk, and the mass of the Higgs that is related to the coupling set 1 times b squared. So now I have to emphasize other amazing properties of standard model Higgs sector that you know very well, but but unimportant for what I'm going to tell you later. So you remember in the standard model, we add interactions with fermions in a totally arbitrary way. We put arbitrary 3 by 3 Yukawa matrix interactions, where these Yukawas can be complex. And then what we do is we give a Higgs a vacuum expectation value, and this becomes a mass matrix that is complex, and we have to diagonalize it. Yeah. But due to the fact that the mass and Yukawa matrix are proportional to each other, once I diagonalize the mass matrix, I also diagonalize the Yukawas. Is this relation of proportionality between the Yukawas and the Higgses that tells me that once I diagonalize the mass matrix, all the Higgs couplings will become diagonal. So we have Higgs to coupling to mu plus mu minus, but not Higgs coupling to mu plus tau minus, for instance. Yeah? All the couplings are diagonal. And in general, there are no three flavor changing neutral currents associated with the Higgs, just like happened with the set. No three-layer CP violation. All these effects occur at the loop level. And via the Chadwick interactions that are proportional to CK matrix elements, as you know in the standard model. And this is totally amazing, yeah, because you start with totally arbitrary couplings that can be complex, and it's this mechanism of the diagonalization and the proportionality of Higgs masses to the vacuum expectation value that tells you that there will not be any weird couplings of the Higgs to fermions. Now, this is automatically broken once you add a second Higgs doublet. And the reason that now the mass will be the sum of the Yukawas on one Higgs with the vacuum expectation value of that Higgs, plus the Yukawa to the other Higgs, that is the vacuum expectation value of the Higgs. So when I diagonalize the mass matrix, I will not be diagonalizing each individual coupling of the Higgs to the fermions. And then flavor change in neutral currents could occur. So the way that people have solved this problem in the past is assuming that each fermion species, let's say the up quarks, the down quarks, or the leptons, couple to a single Higgs and not to the other. And that defined then the so-called type of two Higgs-Allen models. Then you assume that one type of fermions couple to one Higgs and not to the other. And this leads to modifications of the couplings that are governed by this parameter cosine beta minus alpha, that if you take couplings to only the field H2, for instance, that is the one that acquires vacuum expectation value V2, so you obtain the modifications of the couplings to those fermions are given by sine beta minus alpha, that will become 1 in this, if you have a standard model case, so in the alignment limit, where Z6 is equal to 0, plus a correction that is governed by 1 over tangent. And if you take fermion fields that couple to H1 that acquires masses proportional to V1, the corrections to the masses of those fermions, so then to the couplings of those fermions kappa B, that is the ratio of the coupling with respect to the standard model value, will be governed by sine beta minus alpha, that goes to 1, again is the alignment limit, minus tangent beta times cosine beta minus alpha. So in the so-called type 2 Higgs-Allen models, what you have is up quark coupled to H2 and down quark coupled to H1, and they have different corrections. In the so-called type 1 to Higgs-Allen models, both couples to H1, and their all corrections are proportional to 1 over cotangent beta, while the couplings to vector bosons kappa B are close to 1, if you want the fermions not to differ too much from the standard model couplings. Anyway, in this framework, I want to reemphasize that the physical fermion H, that is the one that couples with coupling modifiers denoted by kappa T, kappa B, and kappa B, is simply sin beta minus alpha H1 plus cosine beta minus alpha H2, where H1 is the one that has standard model like properties. So there has been, therefore, due to the good agreement of the Fermi coupling with standard model, one can put constraints on cosine beta minus alpha. For instance, if you consider the so-called type 1 two Higgs models, where all the modifications of the couplings are proportional to 1 over tangent beta, then you can go comfortably to larger values of tangent beta and accommodate larger deviations of cosine beta minus alpha from 0. However, for type 2 Higgs models, so then where they are the bottom coupling in particular can differ by large amounts with respect to the standard model because of tangent beta enhancement. So the constraints on cosine beta minus alpha are much stronger. So
Sorry, can I ask you?
Please.
In the previous slide, I didn't understand the alignment limit. So if you apply the alignment, you have that the down type quark couples to H1 and H2 to the top or up type quarks, right?
Well, let's see. The couplings to which fermion they couple is an arbitrary decision, right? So in type 2, what happens is that up quarks couples to the field H2 and down quarks to the field H1. And therefore, but what I'm saying is that whatever you do, then this will be universal. I mean, if I change the type and I decide that both up and down couples to H2 or H1, what I will find is modifications like the ones that I'm depicting here. And all of them in the alignment limit goes to 1. Because in the alignment limit, cosine beta minus alpha is equal to 0, but sine beta minus alpha therefore goes to 1. Yeah.
Yes.
So, make sense? But
yes.
Yes. So tell me.
No, sorry. Continue.
No, it's important. So ask me.
In the next slide, so you are showing the allowed regions.
Yeah. Then the most important coupling that governs the all branching ratios is the bottom coupling, because the bottom coupling is the one that the bottom is the heaviest particle that can decay on shell with respect to a Higgs. The other particles, like the W, the C, and the top, are too heavy to decay from the Higgs. So a modification of the bottom coupling, that is the largest coupling, is the largest branching ratio of the case of the Higgs, therefore, has immediate impact on all the other branching ratios and on Higgs properties. So you want that not to differ too much from the standard model. And in type 2 Higgs models, that modification is proportional to tangent beta. So therefore, large values of tangent beta will be very restricted for a given value of cosine beta minus alpha. And that is what you see, what you see in this plot. You see then when I want to defer tangent beta with respect to the standard model values, I suddenly find that the cosine beta minus alpha cannot be very large. So so it becomes more restrictive than the case of type 1 Higgs model, where the bottom coupling has 1 over tangent beta suppressed corrections. For lower values of tangent beta, other corrections become important, like the top, etc. But then you can tame these corrections so in a better way. Yeah. So anyway, what I wanted to emphasize here is that not only you find corrections proportional to cosine beta minus alpha, but once you have cosine beta minus alpha, then you may have, and sorry, I apologize for this slide, but let me go through it. Here I am assuming that each fermion couples to both of the Higgses. Therefore, there is a coupling here that is Y2 bar that is here that relates to, in the case where the dominant coupling is to H1, that is what I'm plotting here above. So then relates to the form of the coupling Y2, so the one that I introduced, the subleading coupling, in the basis where I diagonalize the fermions. So that coupling in general will not be diagonal. I will induce favorability in the case of the Higgs. But that favorability, so that is denoted by this second line in the first coupling, so will be proportional still to cosine beta minus alpha, because when cosine beta minus alpha is equal to 0, I should recover standard model-like properties. So I should recover that the Higgs couples only to diagonal elements. And then if you look at the first line, put delta, what I call here delta equal to 0, what I obtain is the modification of the diagonal couplings that I defined before, sin beta minus alpha minus cosine beta times sin beta. And the same applies to the second line. My emphasis here is simply that in order to have flavor-relating couplings of the Higgs, of what I mentioned in Higgs, I need two things. First, I need to have a second Yukawa coupling, so a coupling to both H1 and H2. And second, I need to depart from the alignment limit, the cosine beta minus alpha. So these are called, so then the first one is called flavor misalignment, that the coupling Y2 is different from Y1, so in flavor space. And the other is the Higgs misalignment, where denotes the departure of the Higgs properties with respect to the standard model ones. So I need both of things to be different from 0. So I need to have both flavor and Higgs misalignment. And the only reason why I'm mentioning this, and I will not come back to this in the talk, is that, so we have been trying to measure if there is any deviation of the Higgs couplings with respect to the diagonal form. So we are looking for Higgs at Atlas, for instance, Higgs going to mu tau, in Higgs going to E tau as possibilities. Yeah. And right now, Atlas, at least, is finding a slight deviation, not meaningful, of course, with respect to 0. So they are observing small branching ratios into off-diagonal elements like mu tau and E tau. The branching ratio for those decays are of order of 0.1%, so 1 per mil. And the deviation is still not meaningful. It's only 2 sigma. And let me mention only then that CMS is looking for similar decays, and they don't observe any meaningful deviation, any meaningful signal in mu tau and E tau, but they are able to put a bound of order 0.15%. So therefore, it's not ruling out the measurement of Atlas, but tells you that probably if there is a deviation, will be smaller than the one suggested by this plot. Yeah. So then, but anyway, this is an interesting thing. If we see a sizable deviation, a sizable branching ratio into off-diagonal elements, that will automatically tell you that there must be new physics. For instance, like the form that I described into his elements. Questions? Okay.
Carlos, I have a question. And there have been some analysis for Higgs mu E, or at the moment Atlas has not found any value.
They are also searching for mu E. Nothing significant has appeared there. Yeah. So this the only reason why I'm showing this is the only one that has a significant deviation, if you want, with respect to the standard model. And again, don't take it as a hint yet. Yeah, it's probably a fluctuation, right? But it's interesting that this is there. But as I said, the best way of checking if something is true or not is looking at the other experiment. Yeah, and CMS has a little bit less sensitivity, but is not seeing anything in this channel. However, I wanted to emphasize that if you play with this, and I have been playing with models of flavor, due to constraints on the diagonal couplings, it's very difficult to get off-diagonal couplings that induce branching ratios larger than the ones suggested by Atlas. But what is interesting is that Atlas both Atlas and CMS are starting to test interesting region of parameters that will not be consistent, at least with simple flavor models and the present constraints on the diagonal couplings. So we should follow this. We should pay attention to this. Unfortunately, progress will be slow because the luminosity is only increasing by maybe a factor 1 or 2 in the next years. But one should follow this and pay attention to these possible deviations of the standard model. Okay, there are also non-standard Higgs couplings, and here I want to go very fast because I want to go to a question of alignment later. But again, delta put it to 0. What is interesting is that the non-standard Higgses can couple with the, for instance, fermions of the standard model, like the bottom, with couplings that are tangent beta enhanced. So when sine beta, imagine cosine beta is equal to 0, sine beta is equal to 1, and delta is equal to 0. You have a tangent beta enhancement of the coupling of the non-standard Higgs with respect to the standard model value. And in particular, if you take the bottom to be that one, like happens in type 2 Higgs island models, you can have an enhancement in the production of these Higgses induced by this tangent beta enhancement. And in particular, you can produce non-standard Higgses in associated production with the bottom, for instance, by using this tangent beta enhancement, or you can induce the production of these non-standard Higgses via gluon fusion mediated by the bottom, again, due to this tangent beta enhancement. And then this explains why, so the bounds on these non-standard Higgses, so then are increasing this type of Higgs models with tangent beta. So let me show you, for instance, an example. So if you go to CMS or Atlas, you will see plots like this, where you find bounds on the mass of the non-standard Higgses that become stronger and stronger as the Higgs becomes, as tangent beta increases. And here you see, for instance, this plot where on the left, where you have the bounds on the Higgs that can go up to almost 2 TeV, so then when tangent beta is large, of order 60. 60 is an interesting value because at that point, the bottom coupling that appears in the Lagrangian becomes equal to the top Yukawa coupling. So 60 is a value suggested by models of Yukawa unification. Another thing that I want to emphasize is that you see the dashed line. The dashed line is the expected limit. What they were expected just if they don't see any signal. But the observed limit is a little bit weaker than the expected limit. So there is a small excess. And this excess is at the 2 sigma level. And this, by the way, searches for productions of Higgs mediated by bottoms, like the one that I denoted here, with subsequent decays of these non-standard Higgses into taus. And this assumes type 2 Higgs island models where both the down quarks, bottoms in particular, and taus has this tangent beta enhancement. And then allows you to do efficient searches for these particles. Anyway, by the way, again, here there is an excess in CMS, but no similar excess appears at Atlas. Again, so let me just comment on the searching for new Higgses. There have been searching for Higgs to photons, decaying to photons, just like the standard model that decays into photons. Maybe there can be a new Higgs decaying into photons. And therefore, these searches, they do bin by bin, and they see if they see a photon excess. And there is an interesting hint at 95 GeV that appear for a resonance decaying to 2 photons at CMS. Again, Atlas has not seen any particular deviation. So CMS is an excess at the order of 3 sigmas. But Atlas, unfortunately, has seen an excess in the same channel that I would not even call an excess at the 1.5 sigma level. Yeah. So there is an interesting excess that has not been confirmed by Atlas, has not been ruled out by Atlas either, because Atlas has a little bit less sensitivity. But some people find this exciting. So then there could be a new Higgs, and that they came to 2 gammas with a mass of 495 GeV. There is another search for similar to what I described. So Higgs decaying to tau tau. I mentioned that there is a potential in excess. You can see this excess on the left, and this is broad excess about 1 TeV. That is the excess that controls this departure of the observed from the expected limits. And you see it's very broad, with masses that can go all the way from 400 GeV to 2 TeV. And there is another intriguing excess close to 100 GeV, so close to the 95 GeV that we mentioned before, that some people see it as an evidence that maybe it's the same particle, that the same Higgs particle decays both into gamma gamma and into tau tau. Again, I will take all this with a grain of salt. I don't believe that one can be too excited about this, but the fact that the 2 excesses are around the same mass is intriguing. And there is also an excess at LEP around the same mass, that some people see it as evidence that maybe there is something in that mass relation.
What's the difference between the 2 plots? One is with the gluon.
Right. Exactly. It's the production state, and they can differentiate the production state because they can look for bottoms in the final state or no bottoms in the final state. Yeah, and then so therefore, again, I would not take this as a hint of new physics, but you see this excess in the gluon fusion final state. I wouldn't say that there is anything interesting in the bottom production. Again, but again, interesting. By the way, the gluon fusion can be mediated by both top and bottom. So you can go to a model where you add a singlet to a spectrum that mixes with standard model Higgs, and the singlet is produced via mixing. And there are many people who have written articles in this direction, trying to interpret this 95 GeV Higgs, trying to make it decay to photons, BB bar, to explain the LEP excess that again is as marginal as all these excesses, and the tau. So it seems that to explain the 3 simultaneous is very hard, but to explain 5 gamma gamma and tau tau simultaneously, or gamma gamma and BB, is possible. So it's possible without too much effort. Okay, now, I told you that I can go from the general basis to the Higgs basis by doing this rotation in tangent beta. That modify all the quartic couplings. And I just want to pay attention to the coupling that I denote here as lambda 6. If you want to go from the original basis to the Higgs basis, this gives the relation. If you want to go in the other direction, you want to relate the set to the lambdas. The relations are the same by changing beta by minus beta. So then why I'm saying this is related to what I'm going to show you in a second, and I reiterate it again. So if I want to get the relation Z6 that controls alignment with the original couplings, This is the formula that connects them, and that is all what matters in what I'm going to tell you. So the question is, how do you get alignment? If you want to put a second Higgs doublet, and you don't want to decouple it, you want to send the mass to very, very large values, but you still want to have standard model-like properties, what you demand is, for some reason, Z6 should be 0, or should be small. Yeah. But why? In principle, Z6, as I'm showing you, has a certain arbitrary dependence on lambda 1, lambda 2, lambda 3. So there is no reason why Z6 should be small. Yeah. So only in certain particular conditions, Z6 will be small and alignment will be achieved. And to make a long story short, so alignment will be obtained in certain particular conditions. One conditions will be, and they are realized in different models. One condition will be an accidental cancellation. And then, for instance, at large tangent beta, lambda 2 governs the Higgs mass. Lambda 2 is Z1. It becomes Z1. This Y2 and 1, 2 is converted into 1 is notation. But this standard notation. So, and you can have that. If you look at what happens at large tangent beta, all lambda 1, lambda 3, lambda 4, lambda 5, etc., are all suppressed because by one factor of tangent beta or two factors of tangent beta. Cosine beta square is 1 over tangent beta square. Sine 2 beta goes like 2 over tangent beta. So then at large tangent beta, alignment could occur is lambda 7 that is not suppressed because sine beta and sine 3 beta goes to 1 and minus 1 in that limit, in the limit of large tangent beta. If there is an accidental cancellation between what I don't know here, lambda 7, and what happens with lambda 2, lambda 3, and lambda 5. And then that cancellation occurs in the MSSM, for instance, the mean supersymmetric standard model. What happens is that lambda 7 is occur at the loop level, but the tangent beta cancels the loop suppression, and there is an accidental cancellation with other Higgs couplings. For small tangent beta instead, so the lambda 7 term can be neglected, and there may be alignment, for instance, when lambda 1 is equal to lambda 2, equal to lambda 3, lambda 4, and lambda 5, due to the fact that when lambda 1 and lambda 2 are equal, so then what you find as a common factor is just sine beta square minus cosine beta square, that is minus cosine 2 beta. And that could be related to symmetries. I mean, these relations of the different couplings can be obtained by symmetries. And finally, for large tangent beta, you can have lambda 7 negligible, but you can still have a cancellation if there is a relation between mh squared and lambda 3, lambda 4, and lambda 5. So, as I said, none of these conditions appear in an automatic way. Yeah. And let me tell you one example in which this happens, that is the MSSM. So then, because this condition that I denoted at the end appears an emergent condition in the infrared by some miraculous coincidence. So as I said, if I put supersymmetry and not go to supersymmetry, you can get this alignment at the loop level. But it's interesting that in NMSSM, where you add to the standard model a singlet in the supersymmetric way, so you can have that the mass is governed by this coupling lambda, but also Z6 is governed by this coupling lambda. And amazingly enough, for the same lambdas that you obtain the proper mass, ignoring loop corrections, you also obtain that the coupling of Z6 is reduced by accidental coincidence. And those, let me show you what happens. And here the value of lambda that you need for that is depicted at the bottom of the transparency, and is given by this relation. If you want Z6 equal to 0, ignoring loop corrections, what should happen is that lambda square should be equal to mh square minus mz square cosine 2 beta over b square sine square beta. So all things are known apart from beta. But when you depict what is the value of lambda associated with this as a function of tangent beta, you obtain that lambda should be in a narrow range. That is around 0.7. So something like 0.68 plus minus 0.04. So are the values that you need for set 6 to cancel. And at the same time, you get the proper mass, 125 plus minus 3 GB. Now, how do you obtain these values of lambda? Well, it turns out that in NSSM, so then if you take these values of lambda, you obtain that the couplings of all particles to the standard model, to the couplings of the Higgs, standard model Higgs, standard model light Higgs to all couplings become very close to 1, very close to the standard model prediction. Kappa becomes very close to 1 due to the fact that sec 6 is very close to 0. And this is denoted, for instance, in the plot. Now, the way of getting those values of lambda is, let me forget this, is that there is an infrared fixed point of this coupling. So if you start with a coupling of order 1 at high energies, it turns out that, amazingly enough, there is an infrared fixed point that drives it to values of order 0.65. So infrared fixed point means that no matter from which values that you start at the unification scale, and this is denoted by solid lines, you converge at low energies to values of order 0.7. And this is an amazing property that leads to alignment in an emergent way. Anyway, there are other ways of getting alignment. Forget this. One is related to entanglement suppression that I will only talk about this if you have questions later, but because it's totally orthogonal to all what I have said, apart from the fact that you can get alignment associated with entanglement suppression. Let me end this talk instead of talking about something else, that is the self-coupling of the Higgs. You know, an important property of the Higgs is related to the Higgs self-couplings, because right now we don't have too much information about the Higgs potential. We only know the minimum related to the vacuum expectation value and the curvature around the minimum related to the mass of the Higgs. But if you want to go to further properties, you want to test the Higgs potential, you want to test the trivial coupling that is originated from the quartic coupling of the Higgs. It turns out that if you go to the vacuum expectation value, so to the minimum, the Higgs can be expanded, the Higgs potential can be expanded around the vacuum expectation value, and you obtain trilinear couplings that and quadrilinear couplings that have to do with the quartic coupling lambda. Now, the quartic coupling lambda can be related to the Higgs mass, and sorry, there is an mh square missing in the last term of the potential. And in particular, the Higgs trivial coupling that can be derived from the potential is related to the mass of the Higgs and the vacuum expectation value. So if you have the Higgs potential, this condition should be fulfilled. So then a good way of testing the potential of the standard model is to testing deviations of the trivial coupling with respect to the standard model, relation of the trivial coupling of the Higgs with respect to the specific relation with the Higgs mass and the vacuum expectation value of the Higgs. And that can be done. That can be done at LHC by testing double Higgs production. And the reason is that if you take double Higgs production, so this can be mediated by loop effects mediated by the top, like single Higgs production, or so diagrams that involve the trivial coupling, like the one that I'm depicting here. And the people have made a lot of effort in trying to find the value of the cross-section of double Higgs production, so as a function of the coupling, deviations of the trivial coupling with respect to the standard model. And this is what I'm denoting here with the gray lines at the top. They are similar deviations in weak boson fusion, but involves not the coupling to the top, but the coupling to the W. But you see that there is a very funny dependence of the production cross-section that becomes minimum for values of the ratios lambda with respect to the standard model, the trivial coupling with respect to the standard model of order 2.5, and then increases for smaller values, and in particular the standard model value, so becomes somewhat larger than the values that you obtain from 2.5, yeah? And then increases for smaller values and increases again for larger values than 2.5. And again, right now, we have very little information. I will show you what we know about the linear coupling at the LHC. So before doing that, let me mention that this production cross-section suffers, of course, so from deviations of the linear coupling, but also possible deviations of the top Yukawa coupling. So in order to really get information on the linear coupling, you have to know also the top Yukawa coupling very, very well, because unfortunately that coupling involved the top is dominant. So small deviations of the top Yukawa coupling can lead to a large deviation of the double Higgs production. And this is what I'm depicting here. For instance, in the orange line, I just set the linear coupling to be equal to the standard model linear coupling, and there is the coupling to the top, denoted by kappa top. And you see that there can be a large deviation with respect to the standard model prediction then of the Higgs cross-section, that is when I put kappa t equal to 1 in this case, and in the orange case, simply associated with a small deviation of kappa top, of the order of the ignorance that we have right now. And simultaneously, in order to get a large deviation playing with lambda, I have to go to much larger deviations. So for instance, lambda 3 equal to 2.5, lambda 3 of the standard model, linear coupling, give me to the blue lines, and 0, that is still a possibility, give me to the orange line. So therefore, when you do the fit to kappa lambda based on present LHC data, you have to combine single and double Higgs productions. Because the single Higgs production will give you information about kappa top, and double Higgs production will give you the ulterior information about kappa lambda that you want to know. So, and there are these fits that you can see here. You see the scales. The scale in kappa lambda, kappa top are totally different. The scale of kappa lambda goes from -10 to 20. And the scale of kappa top goes to small deviations between 0.9 and 1.4. Yeah. And this is related to the sensitivity that you have right now for single and double Higgs production. You see, if I take single and double Higgs production combined, and I combine the double Higgs production that gives mostly the sensitivity to kappa lambda, and the Higgs production, the single Higgs production that gives the sensitivity to kappa top, right now I can constrain kappa lambda only between values of order 10, so for a 6 in this case, and 0, yeah, in the best fit, while kappa top can be constrained from values from 0.9 to 1.1. Now, this study will become increasingly important at higher luminosities. So right now, we believe that if we go to 3 inverse Atoban, we will be able to constrain kappa lambda, so the linear coupling, and therefore the quartic coupling of Higgs potential, to values that differ by 50% with respect to the standard model values. So not between 0 and 6, but between values that are a little bit lower than 1 and values of order 1.5. Yeah. So we'll get a much better information about the standard model constraints on this coupling. Okay, so let me conclude here, because yes. So we have shown that precision estimation show a good agreement of all couplings with respect to the standard model expectation. Two Higgs model single extension provide a good effective field theory to the status of LHC data. And if I have line non-standard Higgs bosons we will demand alignment in field space. I discussed a few ways in which alignment can be obtained, in particular in the NMSSM. And surprisingly, well, that I didn't mention, I didn't explain, quantum information methods also can lead to alignment, although the phenomenology is somewhat unclear. So that's why I didn't cover it in detail. So let me conclude by saying that I believe that Higgs physics remains as the most vibrant field of particle physics, one in which many surprises may lay ahead, and which may have profound implications for understanding of nature. Okay, thank you very much.
Much, Carlos, for the very nice and very complete talk. Question from the audience? Carlos, in this next to minimal supersymmetric standard model, if one consider, for example, radiative correction, how this alignment limit could be modified, this alignment limit condition will be...
Yeah. Let me tell you, and I made a mistake. There it was. So let me go again. Okay, so then
for this C6, because there is
this
C4.
Okay, this plot that I depicted here is including full radiative corrections. Yeah. So then there are many important radiative corrections. Ones that include, one that relate to the mass of the Higgs that is affected, and also the radiative corrections induced by the couplings, and both have to be included. Then this plot that I'm showing you here is taking, there's a program called NMSSM tools, and then that includes all the full radiative corrections that you can have in the model, and you study what happens with the couplings with respect to the standard model, and you see that still, so there is very little influence of this radiative correction, and you can still get values that are very close to 1. Then for values of lambda that are close to 0.65. Yeah.
Very nice. Thank you, Carlos.
Yeah.
More questions from the audience? Another question, Carlos. In this, here in that analysis, you are assuming CP violating scalar potential.
Generically, I mean, here, I assume CP violation.
Yes. So H2 should be the pseudoscalar, the CP of the scalar should be H2.
H3 in this case is a pseudoscalar. Then there are in mixes with the CP scalar via the imaginary component of the quartic couplings. And therefore, when these imaginary components are small, this vanishes. If these imaginary components are not small, what I have immediately is consequence for electric dipole moment. Yeah. So, and that have been done, and that put constraints on this, the possibility of this imaginary component. Actually, I have a different talk on this, but I decided to exclude this subject. But yes, in general, there is CP violation. If you put couplings, you remember this couplings lambda field, lambda 6 and lambda 7.
Yes, I see.
That can be very important in determining the properties, the phenomenological properties. If I put complex values for these couplings that are allowed, in principle, then what I obtain is an admixture of the CPN and CPO components. Suddenly, both Higgses will acquire, or the three Higgses in general, will acquire not only psi bar psi couplings, but also psi bar gamma psi couplings. And that induces, in general, CP violating effects. Yeah, and those CPLA effects, the most serious one are electric dipole moments. Yeah. Now there are several ways of canceling electric dipole moments. These small imaginary components can serve to generate baryogenesis, but under the constraints that you don't upset the electric dipole moment constraints. Yeah.
So it is fitting baryogenesis will give attention to with the electric dipole moment and vice versa. Will not be
That is
possible to
correct.
fit both at the same time.
Yeah, that depends on where you put the electric dipole moment constraint. So a way of generating baryogenesis without upsetting electric dipole moments is to switch on the coupling to tau. Then, for instance, and keeping the coupling to electron and muon at bay. This is not what happens, however, here, because if you induce separaton by mixing, you will induce separating couplings to all fermions, to the 3 generations. So therefore, there, as you say, then if I want to generate baryogenesis via the coupling to 3rd generation fermions, separating coupling, then I will have to face the constraints induced by the coupling to the 1st and 2nd generation. Yeah. And those are strong. So therefore, we have to go to a delicate balance of trying to generate baryogenesis via these couplings and canceling electric dipole moment effects. Yeah.
Thank you very much, Carlos. More questions from the audience?
I would like to ask you, okay, you have talked about this second Higgs doublet. What about singlets and triplets of SU2?
Yes. So then actually, one of the important things is that if you want to accommodate, for instance, Higgs to gamma gamma, or when you go to NMSSM, you suddenly get singlets. Yeah, and those singlets are can be lighter and can be present. So and give important phonological corrections like the one that appears here, right? So then those are allowed, of course, are very important. Two Higgs-Allen models is one of the modifications. Triplets also are important. One has to be careful with the background expectation values triplets, not to upset the raw parameter, so precision measurements. But I mean, different from singlets, triplets break electroid symmetry. Yeah, and then and therefore one has to be very careful in not switching on a very large triplet value because that will upset a lot of the things we know. So then, but if you have small background expectation values of the triplets, there is no problem. And then, and yes, for instance, at the point that people were trying to explain the W mass measured at the tevatrons, the triplets had a resurgence, and I believe that they're very important, yes, as a modification. But as I said, they are more dangerous than doublets. Yeah. One has to be careful with triplets because triplets do not induce the standard Yukawa couplings, but that yet they have a back expectation value that affects electroid symmetry breaking, and that cause some concern. And so, but triplets that acquire small back expectation values are okay. Yeah, yeah. And they are part of the standard phenomenology, as you know. Yeah.
And just, I'm not familiar with the two Higgs doublet model, but is there a possibility to couple one of the doublets just to leptons and the other to quarks?
Absolutely.
I don't know.
Yeah.
Yeah.
No, there is no problem with that. Then actually, that is called lepton-specific models. So then, or type 4, yeah. No, there is or type three. Well, I don't remember the denomination, but yes, that
The
can be done.
number.
And actually, to explain, for instance, if you want to explain Higgs to gamma gamma and Higgs to tau tau excesses, you go to one of those lepton specific models, yeah, and then you can do it. Mm. Yeah, no, all this. So provided you couple each Higgs doublet to one particular species of fermions, like up quarks, down quarks, leptons. You can do all the combinations you want. Mm. So then that is simply constrained by phenomenology, mm. But
Oh,
by experiment. But phenomenologically, all those possibilities are perfectly okay. Yeah.
but from supersymmetry, or at least
No,
from the MSSM, you have some
supersymmetry.
constraints on it?
That's correct. So supersymmetry is very peculiar because then all the Yukawa couplings are governed by holomorphicity of the suprapotential. That is the one that leads to the uh, to the fermion couplings. And the problem is that this is due to the charges. So then when you write the superpotential, you have to write all in terms of left-handed fields, and then and the sum of the charges of the down and lepton fields, because they are down kind of fermions. So leads forces to couple to one of the two Higgs doublets, and instead up quarks and neutrinos have to couple to the other Higgs doublets. So because the holomorphicity doesn't allow you to put the Hermitian conjugate of any of those Higgses. In the standard model, for instance, you couple boson and taus, or down quarks and leptons using H, and up quarks and neutrino is using the dual of H. Yeah. But then you can add both couplings using the H conjugate if you want.
Yeah.
But in the supersymmetry you don't have that freedom. Supersymmetry demands that one of the Higgs is coupled to bottom and taus, and the other couples to up and neutrinos. So there is no way out. Is well, at least not in the minimal models. Yeah. So therefore, supersymmetry leads to what is called the type 2 Higgs doublets, where one of the Higgs is the one that is usually called H1, with back expectation of V1, couples to bottom and taus, and therefore have tangent beta enhanced modifications to the couplings, and the up quarks has tangent beta suppressed modifications to the couplings. So because they couple to H2, that is the one that acquires large back expectation value for large tangent beta. Mm. So there is no freedom. Yeah,
Thank you very much.
you're welcome.
More questions from the audience? If there are no more questions, we thank Carlos Wagner
Okay,
for the very nice and very complete talk.
okay, thank you
There is
very
another
much.
question?
Then,
Yes, Carlos?
no, thank you very much for the invitation. A pleasure to do the talk. And okay, I hope to see each other again in the near future. Okay.
Yes, it will be very nice that you can come soon to Chile. Next year there will be the head conference. It will be great that you can come. This is
Okay.
usually the annual workshop. Thank you so
When is
much,
that?
Carlos.
That is when?
We usually had it every
January.
2 years around January, something
January, right?
like
Okay.
6th of January, around that, around the week of 6th of January, more or less.
Okay, I will keep it in mind. I see. Okay.
Thank you so much.
Anyway, thank you, and see you soon. Then keep it
See you
in mind.
soon.
Bye.
Thank you.
Bye.
Bye.
Bye.